crazy update out of China. A research team has developed a method of converting carbon dioxide into starch. Science magazine published this paper from a research team, 100 grams of catalyst converting 5 grams of CO2 per hour into starch. Friedberg, I saw you tweeted that this is 10 times more efficient than corn plants. What's the impact of something like this? Could it hit scale? Would it have an impact on food security, carbon, global warming?
Yeah, so I tweeted this paper out because it's a fantastic demonstration of what's possible in this new not emerging, it's been around for a long time, but kind of, in the state of art in biomanufacturing. Photosynthesis is the system by which most starch is produced on planet Earth today. That is, plants convert sunlight and use water and carbon dioxide to make starches. And starches and sugars, which are what carbohydrates are, account for 60% of human calories. And we get all those calories from rice, wheat, potatoes, which are grown on about 60% of our acres that we farm on planet Earth. So, in plants, there's a series of these chemical reactions. And what these guys did is they isolated and created a couple of specific proteins, which are a class of proteins called enzymes. And what an enzyme is it's a protein that can take different molecules and combine them and force them to react and make something new. And they identified a couple of enzymes and engineered a few enzymes and put them together in a cell-free system, meaning there's no cells involved. It's just a tank with a bunch of fluids in it. And they stick in some carbon dioxide that they can suck in from the atmosphere, and they have to drive it with some hydrogen gas, which we can just get from water. And the system basically converts that carbon dioxide into starch, which is being done at a rate that's almost 10 times higher than what we see with corn plants. So it's an incredible demonstration. There's several steps to the system, like 6 steps. And I did some back of the envelope math, and my back of the envelope math on what they've demonstrated. And by the way, everything they did is publicly available for reproducibility. So people are going to try
open source. Yeah.
Open source. So people are going to try and copy this now. But my back of the envelope math is, this system can produce about 10 grams of starch per liter per day, which would mean it would take about 2.7 trillion liters to suck up all of the carbon dioxide that all of humans are putting in the atmosphere every year from all of industry. That would require about 27 million tanks that are about 40 feet tall and about 8 feet wide. All of those tanks could fit in an area about 25 by 25 miles. You could attach one nuclear reactor to it to suck up the water and convert it into hydrogen gas and feed this system. And those tanks, 25 miles by 25 miles, would take out all of the carbon dioxide on planet Earth and convert it into usable starch. And that starch, by the way, that system could be tuned not just to make starch for consumption. It could be used to make biofuels. It could be used to make bioplastics. It could be used to make anything that's hydrocarbon based. And so you can kind of think about this being the entry point to a series of production systems that we could use to make stuff.
Friedberg, why did they open source it?
So they're a research team of scientists from China, and they've been iterating on this process. This isn't the only process, right? And so what they're showing is that this is possible. And what I think we will see is a lot of people rattling their brains now saying, not only do we use proteins and enzymes that we find in nature, but we're going to start to engineer our own proteins and our own enzymes that are even more efficient than what we see in nature. And that's what's starting to happen. This system alone, what I just described, this 25 mile by 25 mile system, which is tiny, is the equivalent of starch production from 42 US corn belts. If you took all the corn growing in the United States, it's 42 times that is what it would produce. That's my back of the envelope math of kind of what these guys did. And so I think what they're showing is this is
what's
possible.
incredibly, yeah.
Yeah. And the implications, we could go in 100 directions and we could talk for an hour about what this means and what you could do with it. But I think it really catalyzes this point that we're kind of, everyone's always like, how are we going to get all this carbon out of the atmosphere? What are we going to do with this? Where there's a will, there's a way. The science is here today. 27 million tanks made out of plastic. You could probably get that stuff produced, a couple $1 billion. Find a piece of land that's 25 by 25 miles that's near some water and put a nuclear power plant there. and you could suck up all the CO2 in the atmosphere every year.
Anybody want to take a guess of how many people on the team were in advanced math courses?
The funny thing about this that I think is really interesting is that it came at the same week where we were ending, what was this political theater of COP26. Greta Thunberg, who's,
how dare you?
How dare you?
Blah, blah, blah.
She had this very funny comment, which is like, it was a bunch of corporate nonsense and the same old blah, blah, blah was her description of COP26. We had this great trickle of agreements. There was on Monday, there was an agreement to stop deforestation. And then you realize it's a non-binding agreement. And you're like, oh, okay, well, I guess we're not going to stop deforesting. We're just going to keep, doing that. And all of this stuff just kind of took a lot of my enthusiasm. And I was a little despondent about what was going on. And then when I saw this thing, I was really quite impressed. I will say that there's a very tricky thing happening right now, which is that developing countries basically said, listen, if you want us to go after climate change, we want $1.3 trillion a year to support us. And so, the Western world will have to figure out whether we're willing to pay, what is the equivalent of, 6 or 7% of US GDP to a whole bunch of other countries every year for them to slow down. And if we don't make these payments to India and China and a bunch of other developing nations, they have said we're just going to continue to do what we're going to do.
Here's an idea. Take half of that money and put it towards science.
Yeah, take half that money and go build a plant that uses this system that was just demonstrated and put it in South Texas and suck up ocean water and convert that ocean water into hydrogen gas.
Create jobs.
Right? By the way, ocean water can be turned into hydrogen gas by running electricity through it. So you're putting a nuclear power plant to make the electricity. You run it through ocean water. You create hydrogen gas. You pump it into these friggin' tanks. And it sucks up all the CO2 and it makes stuff that humans can consume and that we can use. And suddenly you have this abundance of material, you have this abundance of food, and you can turn this and jobs, and you can turn this into a lot of different things. And this kind of goes to the point I've been making for a while. If we want to invest in infrastructure, this is the sort of thing that both solves climate change, creates jobs, and has extraordinary economic return potential built into it. So,
but how does it get politicians reelected?
I think the private market may come after this stuff. I'll be honest. I'm talking to people looking at this being like, why don't we make a plant that we can make biofuels and bioplastics and food and other stuff out of this technique? And there's going to be other iterations of this technique. But it's such a no-brainer.
What would a prototype cost? Like a functional prototype of this?
Like a small prototype, nothing, right? I mean, a couple $1 million. Yeah, like nothing. So,
the other thing that happened this week beyond this request for $1.3 trillion is that, we're now seriously considering carbon tariffs. And we talked about this on a pod before, but, I've said, I think this is the most disruptive thing in the capital markets and geopolitics that can happen in the next 10 or 20 years is an effective carbon tariff, which is to say that when a good or service enters the borders of a country, they will levy some tax that they think represents its drag on the environment. And so, the simple example would be a car. You make a Tesla in Texas, but the minute it crosses the border to Canada, Canada says, well, here's the true carbon intensity of this car. All of the energy that you put into the aluminum, to the batteries, to the buildings where the engineers sat that were building FSD, and I'm going to charge an $8,000 tax on this car.
Or iPhones coming out of China.
Yeah, that's happening. I think that's coming. So I think that the combination of tariffs and these transfer payments is going to create a real economic incentive for folks to make these kinds of big technological leaps. So I'm pretty bullish on all of that. I'm less bullish on politicians' ability to organize because, unfortunately, again, this is the first time I really paid attention to COP, and it just looked like a bunch of really, useless political theater. Yeah, it was just a lot of political theater.
Sachs, does this science conversation about saving the planet do anything for you? Would you like to get back?
No, I mean, I think it's the way to solve the problem is you have to figure out new technologies to actually take carbon out of the atmosphere because you're not going to do it through, these political programs. I mean, China, India, paying them and other developing nations 1.3 trillion a year. I mean, foreign aid already is one of the least popular parts of the government's budget. You're going to now pay 1.3 trillion to these countries so that It's nonsense. And you're going to pay
Put that
China
money into
on
our
top of it.
education system
Nobody's
and
gonna
create
stand for
science
that.
and technology that solves the problem.
Nobody's
Better
going
money
to stand
spent.
for that. Yeah. And, the
Pour it
taxes
into our
as well.
education system.
Right.
Pour it in.
Yeah. I don't think there's a political solution to this problem that's going to be palatable to people. I think it's going to have to be solved through new technology.
Now, let me ask you a question, Friedberg. You said there's a 6-step process. Given your experience building science and technology products, is it possible for each of those 6 steps to get but 20% more efficient a year?
Yeah, look, I mean, I just say that to describe that there's a series of steps in the system. But at the end of the day, this is a demonstration of science that has been, probably funded to some small amount. But, if you start to iterate on this approach and think big picture and think infrastructure solution here, there's a lot of room for improvement, I'm sure.
So in other words, your back of the envelope 25 by 25 mile, if this is getting 50% more efficient, 25% more efficient year over year, we could see it becoming, twice as efficient every 2 to 3 years. And your 25 mile might be a 5 mile radius city.
I mean, think about going to Mars, right? What are we going to do in Mars? We're not going to grow friggin' fields of corn and grow cows and stuff, right? You're going to need a system that literally takes the molecules that are in the atmosphere there, uses some electricity that's probably going to be produced by a nuclear power plant, and convert those molecules into what you want to make and consume. And that's what we can do on Earth today. The systems are going to get better. They're going to get cheaper. They're going to get faster. And that's why I'm highly optimistic about solutions to climate change in the century. It's not about an if, it's about a when. And, the when is going to be defined by the willpower of how we are going to allocate our people and our capital resources to solve these problems in the near term. We have the tools to do it.